So what is complexity? What I'm going to try and do is section the concept to look at it from a multitude of different angles, which I think is appropriate for any area of inquiry. The way we'll do this is we'll look at complexity as a discipline, the way we might look at physics as a discipline. We'll look at the domain that complexity is investigating. We'll also look at its methods, its epistemology, the kinds of mathematics that you use in complexity science, and then relate it to one of the more fundamental concepts related to complexity, and that's emergence. So complexity in the disciplines. If I asked you to define biology or geography, how would you do it? It's extremely hard to do, and it's no easier for complexity science. So the way to do this, I think, is to break up a discipline into its constituent parts or its preferred methods and approaches. And we're going to do that for a number of disciplines and then finally do it for complexity. So here are some disciplinary traits. How quantitative is a field? Is it obsessed with measurement and calculation, as the natural sciences have tended to be, or is it more satisfied with a qualitative narrative type of account? How reductionist is it? Now, reductionist relates to explanations that feel fulfilling by virtue of presenting the parts of a system. So you go down levels to account for the level of interest. That's what we mean by reductionism. So a physicist might say, to understand gravity, I'd need to understand gravitons, or to understand electricity, electrons, and so forth. Another question which gets confounded with reduction is compression, which is, are the fields amenable to compressive mathematical description? Can you write down short equations that capture the essence of the phenomenon? That's not the same thing as reductionism. It's a different kind of reduction, a reduction to short, compressed equations. And finally, how historicist is the field? How important is history in accounting for a phenomenon? How far back do you have to go? And of course, in biology, we feel you have to go way back to understand traits in organisms. We have phylogenetic explanations. Less so in physics. And so that, if you like, quartet of characteristics helps us to define a discipline. So let's consider physics. So physics is obviously a very quantitative field. Everything is presented in terms of numbers and measurements and so forth. It's also very reductionist because the search for grand unified theories or fundamental theories typically consist in looking for elementary constituents. For example, the standard model in physics, the minimum number of particles and fields. And having done that, presenting that in mathematical terms, using very elegant, very compressed mathematical formula, F equals ma, Maxwell's laws, and so on. So physics has that characteristic that's sometimes described as sort of back-of-the-envelope like calculations, short calculations based on fundamental constituents that are highly quantitative. Okay, so systems biology is highly quantitative. It's also very reductionist. You try to understand traits in terms, for example, of their genetic or epigenetic factors, and it's also very historicist. You understand things in a taxonomical or phylogenetic framework, but it's not very compressive. It doesn't present regularities in terms of very short, elegant mathematical equalities. Then there's something like biological anthropology or biological linguistics, and here they're slightly less quantitative. There's less data than there would be, for example, in genomics. They tend to be reductionist, trying to understand things again in terms of biological factors that contribute to behavior. Very historicist, phylogenetic, and also somewhat compressive, that is using fundamental evolutionary theories, like kin selection, to understand behavior. And having explained all of those, to try and illustrate that all these fields should be understood in terms of how much they weight different factors or traits, where does complexity science fit? Well, complexity science is very quantitative, by and large. It's very historical. We're studying, adaptive agents. And it's very compressive because we're looking for mathematical theories that capture essential regularities. But what we are not is reductionist. Right? We're not looking down levels to explain the level of interest. And that's one of its defining features that we'll come back to at some point when we talk about emergence. So, having talked a little bit about what complexity might mean as a discipline, let's talk about what complexity science studies. That is the domain, the territory of inquiry that establishes the way it looks and feels. So if we look at classical mechanics, physics, this is the study of very ordered processes. And you can write down equations that describe the orbits of the planets and the stars in a very compressive, compact form. That means low complexity. In this case, complexity relates to, in some sense, the number of pages of equations required to describe the regularity of interest. So in that sense, Newton's laws are very compressed. When you get to quantum mechanics, that introduces more stochasticity, more randomness, and the equations, even though they're still classical, are correspondingly slightly more complicated. Interestingly, if you introduce lots of randomness, you can also write down a very compressed description in terms of statistical mechanics and thermodynamics. So these two limits are in some sense the limits of the physical world, and that's why physics has been so effective at theorizing about phenomena. But if you now look at the domain where noise and regularity compete, the complex domain, what happens? We don't really know. We need entirely new kinds of theories to describe this intersection where frozen accidents dominate. That is the world of nature or of culture. And so here's some examples. On the left, classical mechanics, just a little bit more randomness, the wave equation in quantum mechanics. On the far right, where you get a lot of randomness, the description of the entropy of a system. And again, in the middle, where that C is written, some new mathematics, some new description is required that respects the complex domain. Now, what's happened in the 21st century is that two very distinct approaches have evolved to deal with complexity. On the one hand, you have machine learning AI that encodes whole libraries of big data sets with billions of parameters that produce, within a very circumscribed range, highly predictive solutions. On the other hand, you have complexity science, which tries to do something closer to what physics was trying to do. That is, a smaller number of essential processes and equations which describe regularities but don't predict. So it looks as if we've reached this point of bifurcation where you have to make a decision. I can either go down the path of prediction and lose understanding and comprehensibility, or go down the path of mechanism and understanding and lose prediction. And I think the open question that we're all dealing with is, could we reconcile these two different approaches to the complex domain? Here are some examples of methods and frameworks in complexity science that have been invented to deal with the complex domain. And here's three examples. Scaling theory, that is, what patterns or regularities span multiple different orders of magnitude in space and time. Agent-based models, which take seriously the idea of agency or reflexivity. That is, the things that we study in the complex domain have teleology, they have purpose, they have function. And that's not true in physics. A network theory that takes seriously the collective dynamics of complex systems. And of course, one of the interesting things about these three is that they find application. So in scaling theory, we can explain how long organisms live, how many species we typically find in a unit area. We can even apply scaling theory to social phenomena, where we're interested in how patent production, for example, scales as a function of city size. Network theory is used ubiquitously, in this particular case to study political polarization or the spread of disease. And agent-based models are the preferred computational tools for looking at things like swarming, flocking, and congestion in cities. So of interest here is that even though the complex domain doesn't yield to these highly compressive formalisms, they prove to be extremely useful in studying real-world problems. So when we talked about the complex domain, what we were talking about is the structure of reality, what we call ontology. But then there's the question of how we understand that reality, how we describe it, how we mathematize it, the structure of knowledge itself, and we call that epistemology. And complexity science has a very interesting epistemology. In 1960, a prominent physicist working in quantum mechanics, Eugene Wigner, wrote a paper called The Unreasonable Effectiveness of Mathematics in the Physical Sciences. And Wigner was very interested in this perplexing observation that you can invent a mathematics freely through your imagination, and yet somehow that imagination, that imaginary object, can predict regular patterns in the natural world that have nothing to do with you. So how is it that mathematics is so effective at explaining and predicting the real world? And we can place that in a slightly more mathematical framing by saying that what amazed Wigner is that models with very few parameters, that is, highly compressed, very parsimonious models, could predict phenomena very precisely. And that's what's represented on these two axes here, the x-axis showing the number of parameters and the axis coming out towards you, how predictive that model is. And at the top there is an example of what he was amazed by, Maxwell's equations. Here's another example from the founder of the Santa Fe Institute, working in particle physics. This is Murray Gell-Mann. And Murray wrote down a Lie algebra, mathematical formalism, to explain symmetries. In this case, eightfold symmetries, captured by something called SU3. And by manipulating these Lie groups, he was able to predict particles that had never been observed before. So exactly to Wigner's point, somehow the mathematics generated a solution that didn't seem to be present in the mathematics to begin with. Another example is the work of Paul Dirac. This is the Dirac equation. It's a relativistic wave equation. It takes quantum mechanics and special relativity and merges them. And he solved this equation and discovered negative energy states, and he used those solutions to infer the existence of antimatter. So no one has seen antimatter. These equations were derived to describe the ordinary world that we can measure and observe, and yet they predicted something extraordinary. So that's the world, if you like, the epistemological world that's made possible by the simple domains of physics, right? The two edges of that graph I showed earlier, which are either perfectly regular or perfectly random. That's what they allow us to do. But most of the world that we care about, the social world, the biological world, and so on, isn't like that. It has a different ontology, right? It combines noise and order. And so what do we do now? It's not the unreasonable effectiveness of mathematics, it's the unreasonable ineffectiveness of mathematics in dealing with the complex domain. The key to effective coarse graining is that you don't lose predictive efficacy by losing degrees of freedom, by losing parameters. So there are special domains where averaging is actually permitted. And one very good example of that is the domain of scaling. So in scaling theory, you get equations that look a bit like equations from physics. This looks a bit like F equals ma. This is basal metabolic rate scales as mass raised to the 3/4 powers. And those 3s and 4s there are actually the dimensions of space, 3, divided by the dimensions of space plus one fractal dimension. So it's very physical. And you can derive these equations through a mathematics of perturbation theory that would be very familiar to the world of physics. And here's an example of what that looks like. And so scaling theory gives us insights into the complex domain by using the concept of coarse graining very effectively. But again, as I said, for many phenomena, that's not an option. And so much of complexity science does something different. Instead of trying to find parsimonious models like F equals ma or B equals m raised to the 3/4 power, it asks what gives rise to those structures in the first place? What allows for the possibility in the complex domain of coarse graining, or what doesn't? What produces the structure that we want to theorize about? So let me make that quite explicit now with an example. If you think about machine learning and the performance of algorithms like AlphaGo, AlphaZero, underlying all those lines of code and all those hundreds of millions, if not billions of parameters is a very simple idea, the idea of reinforcement learning. And that can be written down in just a few lines of code. That's just a few lines of mathematics. So in that sense, this is highly compressive. It's not the particular model that finally is instantiated, but how the parameters are tuned. And the same thing goes for biology. People sometimes say, evolutionary theory is not predictive. Well, it's not predictive in the sense that you could predict a giraffe or a flea or a bacterium, but all of them were subject to the same optimization principle in their local environment, natural selection and drift. And so what we're looking for is a parsimonious description of the algorithm or the process that produces the object. Physical science theorizes about the object parsimoniously. We're theorizing in some sense about a process that gives rise to an object, a process that gives rise to a theory. So in that sense, complexity science is meta-theoretic. One of the concepts that one hears a lot about when talking about complexity is emergence. It's its nearest relative in a certain sense. And just like complexity, it generates a lot of perplexity. So I want to explain what emergence is now. One very simple way of defining emergence is you're dealing with an emergent phenomenon when there's no need to look under the hood. And I use that in the following sense. If your car stops, you're not quite sure why, and the most natural thing to do is to check whether you've run out of gas. So it's a kind of reductionism there, because you're saying to understand why a car stops, you need to look at its parts. And when a phenomenon is strongly emergent, you don't need to look under the hood. And let me give an example. This equation is the so-called Fermat conjecture, and it took hundreds of years to be solved. And this is Andrew Wiles who finally solved it between 1993 and 95. In fact, the first solution had an error in it, which freaked him out, and then he was able to correct it. But you can ask, how did he do it? How did he solve this theorem? And let me show you quickly some pages from his proof. Here's one page where he establishes the relationship between the Fermat conjecture and elliptical forms. He goes through a whole series of ingenious deductive steps, recruiting unexpected areas of mathematics until he finally arrives at the conclusion, which is the proof of the Fermat conjecture. Now, this proof is presented to us only in terms of mathematics. Right? The language of mathematics is sufficient to establish the credibility of the result. You don't have to look under the hood of Andrew Wiles to determine whether or not this proof is right or not. For example, we don't need to do brain science on Andrew Wiles. We don't have to say, the reason why the proof is correct is because he was expressing a lot of serotonin or dopamine, or this particular neural circuit was being recruited. That would be interesting. That would be something that you might want to know, but it has nothing to do with the correctness of the proof. Similarly, Wiles's economic circumstances, or the particular market that he's working in and the University of Princeton who's paying his salary. None of this is relevant to the correctness of the proof. And neither is his nationality or his ideology. So here's an example where correctness operates entirely at the level of mathematics, and moving below mathematics, for example, doing sort of particle physics on Andrew Wiles's brain, might be interesting, but is not illuminating with respect to whether the theorem has been proved or not. Now, exactly the same thing goes for Go. So here's the code that went into AlphaZero on the left, and here's some algorithms that it's using on the far right. There's the algorithm playing Lee Sedol. If you wanted to understand whether AlphaZero was playing well, you would observe the game. You articulate the strategy and tactics at the level of the game. You wouldn't have to go back down into the code to determine whether or not the move was a good one because this particular for loop was present. Just like Andrew Wiles in the brain, the phenomenon exists at the level of the game, even though all that code is in support of it, as Andrew Wiles's brain was in support of the proof. This raises a very interesting question. Why is it that if my car doesn't reach its destination, we feel it's appropriate to look under the hood? Why is it, for example, in the case of biological psychology or psychiatry, if you're interested in depression or mood swings, you might think it's appropriate to look at the endocrinal system, look under the hood of behavior. But when it comes to mathematics and its correctness, there's no need. And the basic idea here is that there are multiple levels in any complex systems. For example, in the case of AlphaZero, there's hardware, there's computing machines. On that hardware, you have software. For example, you might be running Python or C or Lisp code. But what that code is encoding is strategy. And each of those levels is described by a different language. And each level corresponds to a different kind of understanding. And the key idea here is like the key idea that I mentioned earlier in relation to scaling, which is coarse graining, that as you move from one level to the next, you're projecting many states onto a smaller number of states. So a computer has transistors with many binary states, code has a smaller number of variables, and the strategy space is in some sense the most compact of all. And that's the level in some sense at which theory exists. To the extent that that level operates somewhat autonomously, we often describe that level as a level of a discipline. So that takes us back to the beginning. Ontologically, in terms of the structure of reality, all of reality sits on physics, sits on quantum foam. So ultimately, that's reality. But we don't describe the world exclusively in terms of quantum mechanics. We have theories of harmony and melody, right? We have theories of prosody. We have the theory of evolution. And all of those theories are made possible by emergence. If emergence wasn't operating, then we'd always have to go down to the lowest level, right? And the question then becomes, can we theorize about the mechanisms that make strong emergence possible? So just to make that a bit more explicit, what's implied by emergence is what we sometimes call functional closure or dynamical sufficiency or horizontal entailment. This is the jargon of emergence. And what it's saying is, if you've picked a level that's legitimately emergent, then that's the only level you need to know to understand its future development, right? And that's what this illustration is trying to show. Any given level is necessary and sufficient to predict its own future. So let's just look at the case of Go. So at the highest level, Go is a strategic tactical game. And if you were an expert watching the board, and analyzing the game, there would be no additional value in asking, what computer language was AlphaGo written in? How many for loops were there in the code? Going to the level of the software would not be illuminating in understanding how the game is being played. Similarly, going down another level to the level of hardware, saying, what's that GPU doing when the game is being played? That wouldn't illuminate the progress of the game. It's happening, it's necessary, it's the physical substrate upon which the algorithms and the strategies are being run, but they're not the level at which you would understand the game. And so in this particular diagram, that arrow that goes from one level to the other is signifying that to understand the development of the game, it is sufficient to analyze the state of the board. And that means that Go shows emergence, because I don't need to go down to the level of the software. There's no additional value in terms of the unfolding of the game. And if that were not true, if the only way I could understand what AlphaZero was doing was to look at the state of the hardware, you could argue that's just bad design. There's a bug. There's something wrong with the system. So in fact, in many cases that we're interested in, we're trying to build emergence in. We're trying to build levels that are protected from the lower levels. So when does emergence fail? So we've looked at the case of Go, and we've said that in Go the board is sufficient and that we don't have to look at the software or the hardware. But let's imagine now that you turned up the temperature in the room. You turned it up so high that the cooling system of the GPUs and CPUs failed. And now AlphaZero is producing pathological moves, bugs that are a consequence of overheating. At that point, the board is no longer sufficient. The strategic conception of the game is no longer sufficient. You have to look at the software, and particularly at the hardware, to understand the behavior. And so emergence is an even more subtle concept, because it only applies within a certain range of operational parameters. And when you move outside of that range, then the protection breaks, you get leakage across levels, and you're forced to go down to a lower level. It's partly why in physics, subatomic physics, reductionism, is practiced at very high energy scales, because you're trying to look at the energy scales where you need to do reductionism. And so a big and deep open question is, in the world of complex phenomena, how robust, if you like, is the emergent level? And when are we forced to go down to the more microscopic description? And this is a little bit beyond this discussion, but there are mechanisms that create protectorates. So each of these levels, in some sense, screens off variation at a level below, preventing leakage, which means you don't have to look down. So, for example, a lot of people might study, as I said earlier, psychological phenomena in terms of the endocrine system, hormones. That's a good example where screening off is not taking place, where you don't have protection. So to understand the future of behavior, you'd have to go down and look at the future of physiology, right? And what's so interesting about this is it opens up a dimension of complexity which is a kind of pluralism, because it's suggesting that there could be a science that explains why diversity of epistemology is necessary. So let me just give you two examples of these functionally closed protectorates, one from physics, and that's the ideal gas law. This is a law that relates pressure and volume and temperature, numbers of particles. And this law applies irrespective of the gas that you're studying, right? And the reason why you can write down this equation is because there are theories, Newton's second law, the so-called flux theorem, the equipartition theorem. These are all the mathematical elements that prove protection and say, you know what, you can study the gas at the level of these so-called variables of state, volume, entropy, pressure, temperature. You don't have to go down to the particles and their particular energy states. Another example closer to complex systems is something like zip floor. Zip floor is a very well-known regularity, for example, in bodies of text, that says that there's a relationship between the rank order of a word and its frequency. So, for example, the second most common word in a text is half as common as the most common. The third most common, 1/3 as frequent, and so on. So there's this relationship, it's known as zip floor. Turns out that it doesn't matter what text you study, you find it. And so a little bit like the ideal gas law, there's a set of network theories, combinatorial theories, probabilistic theories that tell you why, irrespective of the text, you expect to find this scaling relationship. So again, this is an instance of mechanisms of protection. So now we can ask a question of how all these things come together. How does the complex domain, the epistemology of complex systems, and emergence relate? And the key point here is that, by and large, when you study complexity science, you're theorizing about emergent levels. And in particular, you're theorizing about those emergent levels using algorithmic theories. And so, if we were theorizing about the mind, we would like to know that it was not necessary to describe the brain. And then we want to know what the variational principle, or the optimization principle, is that's appropriate for mind. So you might have a learning theory that is quite independent of the substrate of the brain. It doesn't really matter, because the mind is a protected state, and to understand its future evolution, you don't need to look at the future evolution of the brain. Now, it might not be true, but then it wouldn't be a truly emergent phenomenon. And so that's how, in some sense, these various concepts come together, and why complexity is so closely related to emergence. Just to sort of conclude here, like everything else, complexity is complex, and there's no simple definition. We can look at it through this lens of a discipline. And that means to look at its characteristics, not to define it, which I find futile. We can look at the world, the ontological reality that complexity sciences are interested in. And that's that world that's perched between order and disorder. We can ask what kinds of mathematics or computation that world requires. That's complexity epistemology. And then how that relates to emergence, and in particular this fact that most of what we study are these emergent properties, that is, new levels of organization which are in themselves sufficient to understand their future states, that they encode a certain kind of entailment such that you don't have to go down levels, as physics does, through reductionism to get a good understanding of how they operate.